Dear friends and dear colleagues, welcome back. This is the second part of the presentation, and now we want to understand how is looking like a mission to Mars. So we developed the trajectories, the orbits, but it's different if we are sending a small probe or if we are sending a big spacecraft with a complete crew. And the difference is in the weight and therefore in the energy. How much fuel, how much load we need to carry, and if we are allowed to send everything at once, or if we need to split into different missions, to different trips. Let's see it together. This is the sequence of the trajectories that we have seen in the previous presentation. So we start from the Earth, we are going to Mars, and then afterwards we are coming back to the Earth. The delta V that we have seen in the previous presentation. Totally 17,000 meters per second. What is our strategy? What we need to carry first? What afterwards? What must be prepared on site? And what we need to bring back? I think the crew must come back, or everybody agrees. The equipment for the stay can remain there, and the Mars landing equipment also can remain in orbit, and the fuel for return must be carried back. What we need for a round trip? We need a crew, MTV, the Mars Transfer Vehicle, then we need the MEV, the Mars Entry Vehicle for landing, then we need the material module, habitation module and equipment, and we need food and oxygen. And for return, we need also the crew, the Mars Entry Vehicle, in this case for Ascent, the return fuel module, the Mars Transfer Vehicle, and the re-entry module, and as well food and oxygen. And those are the travel phases. The Mars Entry Vehicle and the fuel module are sent in advance, and they are waiting in Mars orbit. Phase 4. So the travel from the Earth to Mars, the travel in between the two circular orbits. We have the phase 5, the descent orbit from Mars, where the fuel module is released, the docking with the Mars Entry Vehicle and the crew transfer is achieved, and then the descent and the landing on board at MEV. And eventually the fuel module number 2 and the Mars Transfer Vehicle are waiting in the orbit of Mars. Then the phase 6, the Ascent, where the fuel module 2 is joined with the Mars Transfer Vehicle. The Mars Entry Vehicle raises from Mars. The MEV is docking into MFTV and the crew is transferred. Eventually, the MEV is left in the orbit of Mars. Then the phase 7, where MTV is traveling back to the Earth, and the phase 8, where the crew is landing into the Earth. But first, the fuel module 2 is released after entering the high Earth orbit, the green one, and then the MTV is released when the re-entry module starts the descent orbit here. The Mars Transfer Vehicle can remain in orbit for a future use. We start with some assumptions. We have the 5 modules. The MEV, whose empty mass is 12 tons, the fuel module 84, the material 75, the MTV 20, and the re-entry module 8. 4 people. The oxygen demand 450 liters per day per person. Then everybody needs also solid and liquid food. And we say that 8% is the ratio between mass of the tanks and the shells of the relative fuel. We remember the rocket equation, the The equation says that the mass at the end of the burning is equal to the mass at the beginning times exponential function of minus delta V over C, where the C is the speed of the exhaust gases. And the mass of the fuel is the difference from M0 and M1. The mass of the structure is the mass of the fuel times 8%, as we have seen in the assumption above. And then the initial mass is the payload, so the craft plus food, plus the mass of the previous stage and the mass of the tanks and the shells, the one in the row above. What about the fuel demand of any different stage? The return module, we said, has an empty mass of 8 tons. The shell is 8%, so 0.15. There is no previous stage here, so the starting mass is 8.15. The delta V we know from the table at the slide 3. The specific impulse depending upon the type of motor, which is in this case this value, and then with the formula we calculate the final mass and the fuel as a difference. So we need to go here backwards, starting from the last step and coming into the first one, in order to sum every mass for every step. For the second step, we have the Earth approach, where the spaceship is the sum of the entry module and the MEV. So we have additional mass of 20 plus the shell plus the previous stage 10, which I've calculated before. So the starting mass is 33. Here is delta V, here is specific impulse, the final mass is 66. And so on, up to the trans-Earth injection, we come to a value of 113 tons. For the MTV, we need to make the same procedure and we come to a final mass of 91 tons. And for the Mars travel from the Earth by means of MEV and REM, so the same as above but with different fuel, we come to the mass of 136 tons. And totally we can estimate how much fuel for all those stages are needed, so 241 tons. Our question is which load and where. In the previous slide we have seen that the MEV plus return module plus fuel plus food for outbound travel requires 136 tons at low Earth orbit. The fuel module is calculated as difference between 113 and 30, the empty mass, so it's 83 tons, but at Mars circular orbit. As well as the MTV module is 91 tons, also at Mars circular orbit. And the material module 70 tons at Mars surface. We need to move all the loads at LEO. For the first couple of modules, so this is already done, and we know it is 136. For the fuel module, the 83 must be moved at LEO by means of the same procedures we have seen at the previous slide, and we get 354. Same for MTV, we get 388, and for the material module 391. Altogether 1,300 more or less, and among them 820 is the additional fuel. What is our problem? Our problem is that the rockets we have developed till now are only capable to carry 130 tons at LEO. So we need 10 times this load, and we cannot move all this equipment at once, but we need to assemble in orbit the single spaceships. Let's see how our spacecraft are looking like. This is the MTV plus return module here, and the fuel module here. The fuel module is a difference between outbound and return travel, and it needs to be exchanged at the Mars orbit. And this is the cargo module, which does not carry any crew, but just material or fuel or other spaceships, like, for instance, MTV. And this is the MEV, which is the landing module and descending module. The upper part is for the crew, then we have the lower part, which have this special shape in order to stand with the atmospheric drag. And in the lower part there will be a heat shield which eventually is released during the descent phase to allow the operation of the rockets at the very end of the descent phase, and the rockets are also using for the ascent. And now we come to the question of the questions. Is return travel to Mars today possible? We have seen that we need to match a lot of favorable conditions. First of all, the launch window every 2 years. Then we need a very strict and complex operation sequence, and nothing can be wrong. Then our technology must be reliable, and our teamwork must be proved and very well trained, because it's a very long trip, 900 days. It means only if those conditions are matching, we can have some chance of success. Last but not least, we are not sending a probe, but we are sending people. It's not enough that we know how, but we must know what to do if something unexpected is happening. So, thanks for attendance, thanks for the patience. I hope you really enjoyed it. See you.